So this video is the start of the NET 1010 module. We basically finished everything in ELT 1010, though some of those skills like breadboarding are going to be continued to be worked on through this module. So if you're still a little shaky there, don't worry, we're going to get to it. If we look at our outcomes checklist here, we'll see there's basically 3 outcomes that we're looking at in NET 1010, and your workbook walks you through those 3. And so we're going to start here with truth tables. But before we start looking into that concept, we need to begin with a discussion about digital logic, because that's what NET 1010 is all about, is the fundamentals of digital logic and digital circuit applications. So what do we mean when we're talking about digital and logic? In this context, and in electronics in general, the word digital means something very specific. It means things that can only have 2 states, on or off. Sometimes we think about this as high or low, true or false, a 1 or a 0, voltage or no voltage. Okay, but there's only 2 states that any digital thing can be in. So some examples, a simple example of some digital inputs would be switches. You could consider your house light switch. You can turn it on, you can turn it off, and there's no state in the middle. Okay, you might be able to get the actual switch itself kind of stuck in the middle, but it doesn't make any electrical difference. We also have digital outputs, like your lights themselves, or our LEDs that we've seen already in class, which can either be on or off, and there's no real in-between state. So these are things that we would call digital. And we can simulate some digital logic here. I've got this website open, logic.ly, or Logically, is a digital logic simulator website that you can use for free. And with simple digital inputs like a light switch and digital outputs like a light, we can solve very simple problems, like we want a light to turn on and off with a light switch. That's pretty straightforward. But that's basically as far as this can get us with just digital inputs and digital outputs. What if we want to have a bit more sophistication going on with cases to determine whether or not this light should be on or off? So what can we put in the middle here to accomplish some more complex logical operations, not just if the switch is on, the bulb is on, and if the switch is off, the bulb is off? For example, what if I wanted the bulb to be off when the light switch is on, and vice versa? If I turn the light switch off, the bulb goes on. What if I had another light switch and I wanted the light bulb to only be on if both switches were on, or if only one switch was on and not both? So to accomplish this, we put in the middle here what's called a logic gate. And a logic gate is a combination of hardware that takes some electrical signals and generates an output based on some logic. We're going to look at a lot of examples here. Let's start with that first example I was talking about, where I want this light bulb to be off when the light switch is on. So the first logic gate I'm going to show you is this NOT gate. This is the symbol for a NOT gate here. And all of these symbols we see on the left are just abstract representations of these logic gates. We're going to see later how we actually implement this in hardware. But for now, we'll stick with the theoretical. So this is a NOT gate. This is the symbol. It's a triangle with a little circle on the end. And we'll see later that this little circle is actually just the representation for NOT. So what does a NOT gate do? Well, it's got one input and it's got one output. In this representation of logic gates, inputs always come in on the left and outputs always go out on the right. So we'll hook up our light switch to this input and our light bulb to this output. And we'll see now my light switch is off, but our light bulb is on. And if I turn my light switch off, if I turn my light switch on, the light bulb goes off. So it's inverting the signal. It's taking a true and turning it into a false, or taking a 1 and turning it into a 0. And the opposite as well. It's taking a 0 and turning it into a 1, taking an off and turning it into an on. That's a NOT gate. We're going to look at a few more and start looking at some of these questions in your workbook. So here's our NET 1010 workbook. And the very first page asks you to fill out these truth tables. What a truth table is just a representation of what that logic operator is actually doing. So we can see we have 2 inputs here, A and a B. And A can either be off or on, and B can either be off or on. And in what combination of offs and on do we get an output that is off or on? That's what we're going to fill in this truth table. I've got this website open here, and you can find this information all over the internet. You could look on this exact website or just Google around and you'll find it yourself. But we can see some examples of truth tables for a bunch of different logic gates. So the first one here is the NOT gate. It's a very simple truth table. We've got our only one input, and that if that input is off, the output is on. And if the input is on, the output is off. So that's what that truth table looks like. And again, we see that symbol again here. So I didn't bother including that in your workbook because it's pretty straightforward and simple. Let's take a look at this first one here. And we'll hop back into logically and see what the AND gate can do. The AND gate's this one. It looks kind of like a half capsule. It's got two inputs and one output. And I'm going to go ahead and get another light switch here. And I'm going to hook this up and we're going to see what happens. So I've got my two switches into the inputs of the AND gate, and I've got the output to this light. So if I turn on one of the switches, we'll see that this input is on, but nothing happens to the output. Let's turn that one off and turn this one on, and still nothing to the output. But if I turn both of them on, now the output is on. So the way an AND gate works is the output is not on at all ever unless both inputs are on. Any other combination and the output is 0. So let's take a look at the truth table here. Now on this website, their truth tables are formatted a little bit differently. So it's kind of up to you to convert that into the format in your workbook. But let's take a look here. If input A is 0 and input B is 0, then the output is 0. So if they're both off, output is off. If either one of the inputs are off, the output is also off. But if both inputs are on, the output is also on. And that's exactly what we saw in our simulation. So in your workbook here, we would have a 0 here because A is off and B is off. Here, A is on, but B is still off. So the output is off. Here, A is off, but B is on. So not both of them, so still off. And here, A is on, B is on, so the output is on. So we'd have a 1 here and zeros all over the rest. And that's how you fill in a truth table. Very simple, very straightforward. Notice one thing about the language used here too. This output is on if this is on and this is on. This is an AND gate, and it's this one and this one. So the naming should make sense pretty clearly. Let's take a look at the next one. We're not going to go through all of these together. I'm going to show you 4 of them and leave the other 2 for you to do. So the next one is an OR gate. Let's go take a look. We'll just replace this AND with an OR. OR looks like this. Got these kind of curved lines, looks a bit like the head of a torpedo or something. Let's connect that up, connect that there, and connect it here. So before with our AND gate, when we turn just one of these on, the output didn't turn on. With an OR gate, I turn one of these on, and the output does go on. I can turn that off and turn the other one on, and the output goes on. And if I have both on, the output stays on. What an OR gate is saying is turn the output on if this one is on or this one is on. And there's that language again. It's pretty straightforward. This one or this one or both. That's allowed too. We can look at the truth table here. Here's the truth table in their format. If they're both off, the output's off. But if one of them's on or the other one's on or both of them are on, the output is on. So I'll leave that to you to copy into this format as well. Let's go back to an AND gate. What if I wanted to have AND, but have this light bulb be off as long as it's not this and this? So any other combination but this, I want this to be off. Well, one thing I could do is I could just put in here on the end a NOT gate, connect the output of the AND into the NOT and the output of the NOT into the light. And now we'll see basically the opposite of AND, where the light is on if they're both off, it's on if only one of them's on, it's on if only the other one's on, but as soon as I put both on, it turns off. This is the opposite of AND. This is what we call NOT AND, or NAND. And that's what this is for, the NAND gate. In digital logic, we typically don't do this, an AND gate followed by a NOT, because we have our symbol specifically for NAND, and it just looks like this. Notice it's just an AND with an extra little circle on the end. And remember that circle was the circle from the NOT gate. So that circle means inversion or NOT. So this is an AND gate with a circle, which makes it a NAND gate. And we'll see now it has that same behavior. Output is on as long as both of these aren't on. I turn them both on, output goes off. So what we'll see here, if we fill in our NAND truth table, is that our output is on for all of the cases except for when both inputs are on. So we'll have a 0 here, and these ones will be 1s. And you should notice that it's the exact opposite as our truth table for AND. It's just flipped. Turn all the 0s into 1s and all the 1s into 0s. So with that in mind, you should be able to figure out NOR as well, which is just not OR. And of course, the symbol for not OR is the OR gate with that little circle on the end. I'll leave that one to you. There's one more that I'm going to go over here today, and that's XOR. What is XOR? Well, let's just take a look in here in the simulator and see if we can figure out what XOR is doing. Again, it's just got 2 inputs and an output. We'll hook this up. XOR just looks like an OR, but with this additional little curve thing here. If these are both off, the output is off. If one of them is on, the output is on. If the other one is on, the output is on. But if both are on, the output is off. So what this is saying is turn the output on if we have this one or this one, but not both. So this is what we call XOR, or exclusive OR is what the X stands for. One or the other, but not both. So in your truth tables, when they're both off, no output. If A is on and B is off, we have a 1 on the output. If A is off and B is on, we also have a 1 on the output. But if both are on, the output is off again. So 2 zeros and 2 1s. That's exclusive OR, or XOR. And the very last one that I'm not going to go over is XNOR, which is just an XOR, but inverted. And I'm sure you can figure out that the same way you figured out NOR and NAND. So those are the basic logic gates, the basic logic operations. And we'll see later on in this module that we can combine logic gates in clever and interesting ways to make really interesting things happen. But the first thing we're going to do is figure out how we can create logic gates on the breadboard out of hardware. What do these actually look like in the real world? And can we make them out of just a few components? The answer is yes. So that's coming next.